All right, so now we're going to talk about the Bregman divergence. And before we do that, we first have to talk a little bit about convex functions, because the Bregman divergence is constructed out of convex function. So convex functions and Bregman divergence. And as a reminder, it's like the ever popular Kolbeck-Leibler divergence is an example for Bregman divergence, and it's associated with sort of a convex function, which is very well known as well. Okay, so let me sort of briefly talk about convex functions first. So a function, so a function psi of x, right? Well, I'm sorry, psi of c, right, is said to be convex if the following holds, right? So lambda psi c1 plus 1 minus lambda psi c2 is greater than equal to psi evaluated at the combination of c1 and c2. Okay, what that basically means, if you will, okay, so if you look at this, what's really happening is the following. Okay, so let's say we have some sort of function, okay, and you have a point c1 and c2, right? So this is psi c. So this point is psi c2, and this is psi c1. And yes, then you have some point here, it's like in the interior. I guess I should also say that lambda needs to be between 0 and 1. Okay? All right. So, okay, so you have a point, c1 and c2. And so far, I've just drawn this, it's like in one dimension, but you could imagine that this is in just some higher dimensional space. And so you have a point, it's like, which is somewhere between c1 and c2, and I can write this as lambda c1 plus 1 minus lambda c2 with lambda between 0 and 1, right? So when lambda is 0, right, then you get c2, and lambda is 1, you get c1. Okay, and then as lambda varies from 0 to 1, it's like you get something in between those two things. All right, so again, what you should sort of think of is that you have these 2 points. It's like in this space, and you have a straight line segment that's like joining those 2 points, and you're basically moving along that line segment. Okay, and that point can be written in this form, and you're looking at the function value. It's like of psi. It's like at this point, it's like along this line segment. Okay, so that's the function value here, and I'm comparing it to the linear interpolation of these 2 function values at the endpoints. Okay, and so a function is convex if this linear interpolant at that point is greater than or equal to the function value at that point itself. Okay, so that's what we mean by the function being convex. Okay, and this needs to hold. So it needs to hold for lambda between 0 and 1, and it needs to hold for any points psi 1 and psi no, c1 and c2. Okay, all right. So anyway, so that's what's meant for a function to be convex. So let's now add a little bit more and assume that that convex function is differentiable. Okay, so now consider a differentiable convex function. Then this function is convex if and only if the following is true. So this function is convex if and only if this Hessian matrix which is just given by this second derivative is positive definite. So if you recall your stuff on calculus, it's like then you know this is essentially like the second derivative test, if you will. Okay, but it's generalized to multiple variables because now I'm just not looking at a scalar value function. It's like in one variable, or it's like one direction. It's like it could be defined. It's like on a high dimensional space, and so the analog of the second derivative being sort of positive, right, is that this Hessian matrix is positive definite. Okay, alrighty. So that's the basic idea behind convex functions, right? That if you look at this convex combination of the two endpoints to get something, it's like in the line segment connecting those two, right? Then the function value at that point is sort of bounded from above. It's like by the linear interpolant. It's like between those two function values at the endpoints. Okay. Okay. So that's the basic idea of convexity. It's like, and again, it's like if that convex function is sufficiently differentiable, then we can check that this notion of convexity is equivalent to the Hessian. It's like given by this expression is positive definite. Okay. So there are many examples of convex functions. So examples. So the simplest example probably is something like this. Right, so it's just this sum of squares basically, right? So this is like a sum of squares. We can easily check that this is convex. So this is also half the Euclidean distance, right? Half the square of the Euclidean distance, right? Okay, so let's maybe look at a more interesting example, right? So let's say that we have a P be a probability distribution. Belonging to this n simplex, right? Okay, and if you recall, it's like the reason why we're looking at this n simplex is because it has this normalization condition that the sum of probabilities adds up to 1. Okay, alrighty. So then it's like the entropy is given by the following. So h of p is equal to negative the sum of pi log of pi is a concave function. So it's negative is a convex function. Okay. So this is the Shannon entropy, for example, right? Okay. So and then what's going to happen basically is that, as I said, it's like if you give me a convex function, it's like we're going to be able to construct what's called a Bregman divergence out of that. And then the KL divergence is the Bregman divergence associated with the negative Shannon entropy, which is convex, right? Okay, so that's where we're going off all this. So, so that's one example, right? There's one example here, that's one example here. Let's look at a few more examples. Okay, so so let's look at something coming from probability. So given an exponential family, of probability distributions, okay, and what I mean by that is the following. So I look at some probability x, and there's some parameter theta, right? So this is the exponential of the sum of theta I xi plus some function k of x minus some other function of theta. So where px theta is the probability density function, of a random variable x, and then with parameter sort of a vector parameter theta, and then k of x is clearly a function of x. And then this is a normalization factor. And has the property that it's chosen so that the integral of this probability distribution over the entire domain, right, is equal to 1, right? Okay. All right. So you can check what that is. Okay. So you can check that in order for this normalization condition to hold, it's like you can determine this factor. So this is given by the log of the integral of the exponential of right? Okay, so if you have this, it's like then you can check that when you integrate this probability distribution, you get the normalization condition. Okay. So you can check the following. So you can view this exponential family of probability distributions as a manifold. Where sort of theta is the coordinates. Okay, then you can prove that the Hessian is positive definite. I'm sorry, the Hessian of this function, right? It's positive definite. Okay, and hence this function is convex. Okay, and this is what is known as the cumulant generating function. Okay. In statistics, and it's also known as the free energy in statistical mechanics or physics. Okay, in statistical physics. Okay. And then it's like more generally, it's like this family of exponential functions, right? The exponential family is going to show up. It's like very prominently. It's like in the applications of information geometry. So the exponential family shows up in many applications. Of information geometry. Okay, so all right. So anyway, so these are some examples of convex functions. It's like which play a special role. It's like either in physics, in statistics, and what have you. And then it's like with these convex functions in mind, right? We're going to construct divergence functions out of this through this construction known as the Bregman divergence. So let me just stop here for now.